Okay. Yeah. So this is the yeah. So the period. This is the definition of the period. Okay. So if you get the okay. Now, so once you get the period, you just compute for the inverse of yeah, so you just get the inverse of C modulo R. Okay, so okay, guys, this one is another typo. Okay, this should be C. Yeah, so C times D, which is the so the period here becomes your base of the modulo. Okay, so once you get once you get R, once you get R, you can then compute because you have C. Okay, you have C, then you can compute for D prime. So once you compute D prime, that's good. Yeah. Hi, Joseph. Thank you for coming back. Yeah. So sorry for that.
That's okay.
Yeah. I pressed the wrong button. Yeah. Okay. So the inverse. Once you get so this is the formula for the inverse. So again, we get the R. So you have the ciphertext. Okay. So to compute for R, this is actually very compute intensive. Okay. So once you get R, you can then compute for the inverse, which is D prime. Okay. And then once you get the inverse, you can then raise your encrypted message. You can then multiply it D prime times, okay, to get your original message. So that's the purpose of finding the period. Okay, so because that's the only option you have. I mean, as a cracker, you don't have the private key. Then the only option you have is to get the period, compute the period, which is very hard to do. Okay, that's why you need a quantum computer to do that. Okay, which is precisely the Shor's algorithm. Okay, the Shor's algorithm is a period finding algorithm. Okay, so once you have the period, compute for D prime, and then you can then decrypt the message. Okay. So for example, we encrypted the message using the following numbers. Okay, and the plain text is this one here, and the ciphertext is this one. Okay, we want to use period finding to get from here to here. Okay, so get from the ciphertext to the actual message. So to do that, you compute the period. Okay, so here we want to get the value of R that will make this into 1. Okay, so this is the okay, hold on, I'll just can you hear the noise, or can you hear me, guys?
Yep. Yes, sir.
Okay, I'll just tell them to be quiet.
Yes, yes. Quiet.
So this is your ciphertext. Yes, this is your ciphertext, and what you want to compute is R. Okay, so this is the naive algorithm. Okay, and this one is actually very compute intensive. Okay, so So what does that mean? So for a 2048-bit encryption, okay, there is one source which says that it takes about, for example, if you do this, takes about 300 trillion years, okay, to compute the well, doesn't really say period, but yeah, I think it's the period, because that's how you decrypt the RSA. Okay, in the RSA you don't compute the private key. Okay, you compute the period. So once you do that, so this one is if you use this algorithm, this is very inefficient. Okay, so makes you for very large numbers, n, it takes trillions of years. Okay, hundreds of trillions. So, but because we have a very small number, okay, so we can do this. Okay, so let's okay, we go back to this one here. Yeah, so the period finding. Okay, so this is the so what I'm doing here is I'm generating all R. Okay, so generating all R from 0 to 100. Okay, and then from there, so this one here, I just put it to 100 because I know that the period is I know that the period is less than 100. Okay, and then I'm going to compute for the what you call this. I'm going to exponentiate this. Okay, so 794 raised to the power R, and then I'm going to get the modulo n. And if that is equal to 1, then if the answer is equal to 1, then I can say that I have found the period. Okay. So by the way, guys, this one is very important. You know why? Because this is the one that is being computed in Shor's algorithm. Okay. This is called the modular exponentiation. Okay. So yeah, so that's just remember the term modular exponentiation. So this is your ciphertext, and this is in fact this one here, the for loop here. In Shor's algorithm, the for loop here is nothing but the Hadamard. Okay, but it's not really a for loop. Okay, because in the Hadamard when you what the Hadamard gate does is do a superposition of all values of R, okay, at once. Okay, it's not a for loop, it's at once. So here we just have a for loop because this is that one computer. Okay, but essentially this is how the Shor's algorithm looks like. Okay, initially it will generate all of these numbers. Okay, all of these numbers, and then when you generate all of these numbers at once, some of them have values equal to 1, and that's where you apply already the Fourier transform, quantum Fourier transform, to find the period. Okay, so but I'm getting ahead, so let's run this. Okay, run. Well, it says here the period is 58. Okay, so now I have a period. So let's go back here. And once you get the period, you compute for the inverse for D prime. Okay. So if you take a look at this, you have C, which is R, which is 58. Okay. And then C, which is, what's C? 7. Okay, C is 7. It's 7. C is 7. Okay. So if you have 7 here and you have 58 here, if you substitute m is equal to 3 and d is equal to 5, then you will get this, you will satisfy this equation. So which means d is the number that you are after. Okay, so d is the inverse modulo of c with respect to r. Okay, so once you get d, it's just a matter of getting the power of this one here, which is your encrypted text, to the power 25, which is your d, modulo 3127. And it will give you your original message. Okay, so let's do that. This one here, 794. Okay, just run this. Okay, 1907. Okay, this is your original message. Okay, so that's it. So this is the conclusion. Yeah, so unlike the using a private key, you need to compute for period R and D prime for every block of the ciphertext. Okay. So that's it, no? So this is the RSA practical way of doing it. Okay. So in the next week, next session, we are going to learn why it works. Okay, so why does it work? Okay, so why is it that if I do this, I get the original message? Okay, so that's the theory. Okay, we are going into the theory. And the reason also why we're going into the theory is because the theory itself will allow us to learn why period finding works. Okay, so it will allow us to determine that as well. So that's it. Do you have any other questions? Anyone?
On my answer, I don't have any questions po.
Very good. So yeah, so next week, let's have the theory of RSA. So we'll talk about group theory. Okay, just enough group theory. Okay, it's not difficult, but that will allow us to to be able to explain why RSA works, and that same framework will also allow us to learn why RSA and the elliptic curve, are able to be cracked by the Shor's algorithm because they have the same group structure. Okay, so that's what we will explain next week. Okay, I hope that I'll be able to see you again, but if you can't come, there will be a recording. We will just post this. Okay, thank you guys for attending.
Thanks, everyone.
Thank you. Thanks,
Thank
Dominic.
you.
Bye.
Yeah, thank you.
Thank you. Thank you.